Every large language model you have ever used started as a general purpose model. Trained on entire internet, good at everything, expert at nothing. But the model that is powering your medical documentation assistant isn't the same that is powering your code completion tool. They have been shaped, fine-tuned as per their specific purpose. Hello everyone, welcome back. Today we are going to understand fine-tuning from first principles. What it is, why it works, and most importantly, how to do it without owning a data center. Because using LoRA and QLoRA makes it possible to use a 70 billion model on a consumer grade GPU. So let's get started. So let's first understand why we need fine tuning. Like a base model like Llama 3 with 70 billion has broad general capability. But for specific application, it has some limitations. Like format, it might not reliably output JSON or might add unnecessary preambles. Like sure, I would be happy to help with that, for an example. And the second limitation is domain expertise. Like general medical knowledge is different from knowing your hospital specific documentation format. The third limitation is behavior. Like a customer service bot should be patient and formal. A coding assistant should be direct and technical. Fourth one will be safety and alignment. You might need specific refusals or behavior for your use case. So fine tuning adapts the model to your specific needs using your specific data. So there are three alternatives to fine tuning. First one is prompt engineering, like no training needed, but it is limited. The model weights don't change. The second is RAG, that is retrieval augmented generation. Add external knowledge, like no training required, but it is better for factual grounding. And the third one is fine tuning. It changes the weight, better for format, style, and baked in behavior. So like full fine tuning is also in a very expensive in a way. Like the conceptual simple approach, take all model weights, run your training data through it, and compute gradients, update all the weights. This is called like full fine tuning. The problem is it's as I told, enormously expensive. So for example, for training you need to store model weights of 140 GB for a 70 billion model on a 2 byte of FP16 quantization. And the gradients, another 140 GB of weights. For optimizer state, like for Adam, another 280 to 560 GB, that is momentum plus variance of space you need. And for activation, for backdrop, this varies, but it is also a significant amount of memory. So total you get around 700 GB plus for a 70 billion model. You need around 8 to 6 Hopper 100 or H100 GPUs that each cost around $30,000 on the day I'm recording this video. So just to hold this much of memory. For most people and like most companies, this cost is not bearable and not practical as well. This is why parameter efficient fine tuning or PEFT method exists. So the first one is low array or low rank adaptation. This is the most important fine tuning technique in modern AI as of today. The core insight is when you fine tune a large model, the updates to each weight matrix tend to be like low rank. What does low rank mean here? So a large matrix can often be approximately expressed as the product of two smaller matrices, as you can see in the screen in front of you. Instead of updating like the full weight matrix W, like for example of shape 4096, 4096, that is around 16 million parameters, you freeze W completely. add a bypass delta w, that is equals to b cross a being the shape of 4096 comma r, that is small 4096 comma 8, that is 32k parameter if r is equals to 8. And for the b is of the shape r comma 4096, that is 8 comma 4096, sorry, that is also 32k parameters if r is equals to 8. So total learned parameters for this layer will be equals to 64k instead of 16 million. So during forward pass, output will be equal to 4x plus wx plus ba dot product of ba x, like frozen plus learned updates. And during training, only a and b are updated, w stays frozen. Why does this work? Because fine tuning doesn't need to change the model drastically. The base model already knows language. You are making small structured adjustments. And low rank updates can represent these adjustments efficiently. Like the R we just kept as 8, the rank. Like the rank hyperparameter controls expressiveness versus parameter count. So for r equals to 4, this will be around 0.1 of parameters trained, minimal but fast. For r equals to 8, it will be 0.2%, that is good balance for most tasks. And for r equals to 16, that will be 0.4% more capacity, and r equals to 64, 1.6% across approximately. That's like approaching full fine tuning quality. So where to apply LoRA? So it is typically applied to the attention weight matrices like QKV projections, and sometimes the feed forward neural network layers. Different application benefit from applying it to the different layer types. Like for a 70 billion model, full fine tuning will have around 80 GB of GPU memory requirement. For low array with r equals to 8, this will give 16 GB of require 16 GB of GPU memory. So like for a single A100 or even a consumer grade GPU 3090 or 4090, we can use it like for smaller model as well. So the next thing that is one more technique on this fine tuning is QLoRA, that is quantized low rank adaptation. So this combines quantization with LoRA to push memory efficiency even further. The idea is load the base model in 4-bit normal float 4 quantization, and a new data type that represents normally distributed weights optimally. Then second, it keeps the low RA adapter matrices A and B in FP16, like full precision, and train only the low RA adapters. The quantized base model stays frozen. So why normal float 4 instead of int 4? Because model weights tend to follow a normal or Gaussian distribution. So NF4 or normal float 4 is designed specifically for this distribution. It places quantization levels optimally for normally distributed data, and this minimizes the quantization error. And double quantization like QLoRA also quantizes the quantization constants themselves, the scale factor used to dequantize. This saves another around 0.5 bits per parameters. So the memory requirement for a QLoRA goes something like this. Like for a 7 billion model with rank equals to 8, it will require around 6 GB. And so it can be run on a consumer GPU like RTX 3060. For a 13 billion model with rank 8, QLoRA will require around 10 GB of memory, like for an RTX 3080 or 4080. For a full 70 billion parameter model with rank 8, it will require only 48 GB, like a single A100 80 GB GPU. So instead of getting using 140 GB, it only requires 48 GB. So this democratizes fine tuning. Before QLoRA, fine tuning a 7 billion model required a data center GPU. After like QLoRA technique, we only need any gaming PC. So the quality, like, does a 4-bit quantization hurt the fine-tune quality? The paper showed that a QLoRA fine-tunes model matches, like, or nearly matches full fine-tune quality across most benchmarks. The LoRA adapters are in BS16, so they are trained precisely. Like, only the frozen based model is quantized. The fine tuning adapts an existing model, but distillation creates a small model that mimics a large one. So now we are understanding what a knowledge distillation is. Like, the core idea is you train a small student model to match the output distribution of a large like teacher model, and not just the final predicted tokens, but the full probability distribution over all tokens. Why does this work? Because then, like, why does this work better than just training on ground truth? Let's take a training example. Let's say we have a sentence called "the capital of France is a dash." So the ground truth is Paris. This is the hard label, like just one correct answer. But the teacher distribution is like Paris 98%, Lion or Leon, how it is pronounced. It's 0.5%, Madrid 0.3%. These are like soft labels. So the soft labels contain more information. They reveal the teacher's uncertainty and the relationship between similar answers. The student learns not just what's right, but what's almost right as well. The extra signal from soft labels allow small students model to learn much more efficiently than from a hard label alone, like the ground truth. So there are there are certain types of distillations. The first one is output distillation. Match the teacher's final token probabilities, and it is the simplest approach. The second one is the feature distillation. You match intermediate hidden states, not just the output. It has like richer signal but requires access to teacher internals. And the third one is reasoning distillation. This is for like reasoning models. You generate a chain of thoughts using a powerful teacher like DeepSeek R1 or O1. You train a smaller model to produce similar reasoning traces. So this is how a smaller reasoning model like Quen's QWQ were developed. So some real examples you can take, like Llama 3.1 8 billion parameter that was distilled from Llama 3.1 70 billion reasoning traces. Many small but smart models like Phi series from Microsoft uses aggressive distillation, and DeepSeek R1 released a distilled version across multiple sizes, like from 1.5 billion to 70 billion. And so the next one is the fine tuning pipeline, like how does it goes. So the first is the data collection. The most important step, like garbage in, garbage out, quality over quantity. So like 1,000 high quality example often beats 100,000 low quality ones. Format diversity, like include varied inputs to prevent overfitting. Some negative examples will be include example of what you don't want, optimal but helpful for safety fine tuning. Second is data formatting. Convert your data to a chat format, like role user content. Then second one will be role assistant content, and then we give the content. Apply the model's chat template. Like every model family has its own format. Then the third one is the training step, like using Hugging Face PEFT plus TRL. Load model with bit and bytes quantization for QLoRA. Attach LoRA adapters. Configure SFT trainers, with your dataset, and train for around 1 to 3 epoch. Like more than this often overfits. The fourth step is evaluation. You run your evaluation suite, as explained in video number 12. Like you check target task performance improved, general capability not degraded, and no safety regression is there or not. The fifth step is merging. So after training, you have two components: the base model plus low array adapters. Merge them into a single model, like W merged equals to W plus BA. This gives a standard model that any inference framework can serve. No special low array support needed. Or keep them separate and load the adapters dynamically, like more flexible but slightly slower. The final step is deployment. Your fine-tuned model can now be quantized, GPTQ, AWQ, GGUF, and can be deployed using everything we have learned in this series. So with this video, we have completed the full LLM inference series. So let's take an overview of what we have discussed in this entire series. We started from very bottom, like understanding what inference means, how the forward pass works, and what a GPU is actually doing. Then we climbed through attention mechanisms like KV cache management, quantization, speculative decoding, batching. Then we went deeper into production systems, mixture of experts, multimodal inference, structured output, and evaluation. And we finished at the edge, running models locally, and with fine tuning, making models your own. And now you have a complete mental model of how LLM works, at least theoretically, and how they are optimized, how they are deployed, and how they are even customized. This fields is moving very faster. New paper or new research are coming every week. But the fundamentals we covered, like memory hierarchy, attention complexity, quantization trade-offs, batching strategies, these are the principles that will still be relevant in the future or coming years. So even as the specific techniques are evolving. The theoretical part of the series is done. Next, I might release one video where I can show you practically how LLM inference is done. So if this video or this series helped you in any way, please do subscribe. Thanks for watching. See you next time.